Following up on a number of the previous talks, I'm going to give a talk about artificial general intelligence. And this was the original title of the talk, which I chose because about a year ago I gave a talk called 10 Years to the Singularity. So I figure I didn't want anyone to accuse me of being a liar. So the thing is, it was 10 years to the Singularity if we really try. Now it's 9 years if we really, really try. So the title is going to get mutated year after year. But I still believe this is a reasonable order of magnitude estimate in the sense that if an incredible amount of effort by the right people was put toward developing general intelligence, we could get there. And why I believe that, I'm going to at least allude to during the rest of this talk. Of course, I'm not going to be able to go into full technical details on the various research aspects that I mentioned. A more in-depth title of what I'm going to talk about is here, Artificial Intelligence in Virtual Worlds. So I'm going to talk a bit about AI in general, but a lot of that's been covered by previous speakers. So most of the talk will be devoted to why I think embedding artificial general intelligences in embodied agents in online virtual worlds is sort of the golden path to achieving AGI and bringing about a positive singularity. What do I mean by artificial general intelligence? A number of speakers have gone over this already, and I'm not going to go into too much depth on it. This is a term that's come to the fore really only in the last few years, but it's, of course, a very old concept. And the idea of the AI field from the very beginning, back in the middle of the last century, was to create a real thinking machine, something at the human level of intelligence and then beyond the human level of intelligence. What happened historically, as a number of other speakers have outlined, is most of the AI field sort of went in a different direction, working on highly task-specific, narrow applications, which, as Neil has outlined, in many cases have been extremely valuable for the real world. So I wouldn't want to put them down. But I think it's useful to distinguish general intelligence from these sort of task-specific, narrow AI systems. What I mean by an artificial general intelligence is a system that can achieve a variety of complex goals in a variety of complex situations. Defining that formally and mathematically is a big job, which I tried to do some time ago, and Marcus Hutter, Jürgen Schmidhuber, and other researchers have done with more precision in recent publications. Qualitatively, this comes together with a lot of other things, such as the ability of a system to understand what it is, to understand that it is distinguished from the rest of the world, to understand there are other beings out there interacting with it, and to be able to take a situation in an environment and translate that into a problem that it has to solve, which is quite different than how most of the AI application systems that we see around us work. We look at what Ray Kurzweil has called narrow AI in some of his writings, and you have systems like many of the ones that Neil Jacobstein has described recently, and like a lot of systems that I've built in my career over the last 10 years doing AI consulting work for various businesses and government agencies. These are systems that solve particular problems. In some cases, they solve them very well, much, much better than any human being can solve them. They solve problems that we would qualitatively classify as requiring a lot of intelligence. And these things are a lot of fun to work on. They're cool. They're valuable. They're pretty different from creating a thinking machine that thinks in the same sense that humans do. Some examples of narrow AI, most of which have been discussed already by our other speakers. Deep Blue, it's a great chess program. It's a heck of a lot better than me. It's probably better than anyone here. What it can't do, it can't play Go, it can't play checkers. It can't generalize the strategic knowledge it gained from learning to play chess. Without some tweaks to it, it would probably do terribly at, say, Fischer random chess, where you permute the pieces on the back row in a different order. So there's a lack of a capability to generalize, conceptualize what's learned in one context and transfer it to another context. The DARPA Grand Challenge, which is a lot of fun. I'm very eager to have the other drivers on the road replaced by robots, you know. Still, the nature of the work is that you're really hyper-engineering things to the particular application. It's not like Sebastian Thrun's outstanding car driving software can drive a motorcycle. Yet, if you take someone who's learned to drive a car and put them on a motorcycle, some of them will fall off, but a lot of the car driving knowledge does transfer. The knowledge inside the DARPA Grand Challenge control systems isn't really represented and configured in a transferable, generalizable way, because these aren't AGI systems. Google, I use it many times a day. I think it's a great system. It can answer complex questions. It's interesting, if you type in some simple questions, it actually will answer them for you. You ask them, how long does a giraffe live? You'll probably get the answer, maybe even in the snippets by the first couple questions. But if you ask it, how long does a giraffe not live, you're not going to get the answer. It doesn't really understand what's going on. Now, Barney Pell has outlined technology that moves in the direction of a real understanding of questions, which is the power set technology. And I think that is an interesting case of something sort of building a bridge between narrow AI and AGI, where if you make natural language processing software that gets more and more semantics incrementally, can answer more and more questions, you're getting something that has more and more real understanding. But I still think there's a long way to go between something like power set and something with the human ability to really resolve ambiguous semantics and interpret language in context. And I'll talk a little bit about that a little later. In my own work, over the last 10 years that I've been doing AI stuff in industry, I've done an awful lot of narrow AI stuff too. We made a system called Relics, which is a lot like PowerSet's parser that they got from Park. It takes sentences, outputs semantic structures, and interprets them, and we did this in a government contract. The system was useful. We've done a bunch of biology work, which analyzes gene expression data, single nucleotide polymorphism data, tries to recognize patterns. So you can ask it a question like, what genetically distinguishes people who get chronic fatigue syndrome from others with a similar profile who don't get it? Now, this stuff is very important. I'm proud to have had the chance to be involved in it. On the other hand, you got to do a lot of work to prepare the data to feed into that system. You read papers, you figure out what the important questions are, you pre-process the data, then you run some code, and then you get an answer out, which you then interpret by reading a bunch of research papers, and then you write a paper. So the AI is doing something really important, but it's doing just a tiny bit of the overall research process. It doesn't understand what it's doing. It's analyzing numbers in the same way it would if the numbers came from an oil drilling application or anything else. So this is a graph that came out of some of our biology work. This was actually about mice under calorie restriction. We fed a bunch of gene expression data from mice under calorie restriction and mice not under calorie restriction. You ask it, well, what distinguishes the two genetically? And this is a graph of the gene interactions that distinguish the two. And you can see interesting stuff. You see a gene MRPL12 up there, mitochondrial ribosomal protein 12. It's kind of it's a hub of a little network there. That gene is probably pretty important for why calorie restriction extends life. But this is not an AGI system. It's a narrow AI system. It spits out this diagram. Now it's my problem, or some biologist's problem, to figure out what it means, why it's important, what experiments do you do, and so forth. So I've been undergoing a bit of effort in the last few years to sort of spread the meme of AGI throughout the AI research community. One of the things we did was organize a workshop in Bethesda in 2006, where we had maybe 45 people there, including a number of AI researchers and a number of individuals from the futurist community, which resulted in a book that came out this year, Advances in Artificial General Intelligence, from iOS Press. And following up on that, we're organizing a conference which will be in March in Memphis, Tennessee, at the FedEx Institute and University of Memphis. So I'm giving a quick pitch for this conference, which is AGI 08, the first conference on artificial general intelligence, which is in large part a kind of hardcore technical AGI research conference, but a lot of the themes there are of pretty broad interest to everyone in the audience who's concerned with AI and what it may mean as the future unfolds. So excited about this from the perspective of getting more and more of the research community focusing their minds on the big question of how do you make a thinking machine, as well as the very valuable and interesting questions of building narrow AI systems. So on to the meat of my presentation. How do you create an AGI? Of course, the full answer to that is very technical, and I couldn't tell you in 10 minutes, even if you were all 5 times smarter than anyone on the planet. Well, I still can't. I can tell you, first of all, how I think you can't create AGI. I don't believe you can do it by generalizing narrow AI applications. And I think this is a non-trivial observation. It's a lesson that's come out of the last N decades of AI research, because it wasn't obvious from the beginning that working on theorem proving and chess playing and natural language search and car driving wouldn't be the golden path to AGI. At first, it seemed that it would be. But what we've seen now is you can build specialized programs to do all these tricks. It doesn't tell you much of anything about how to make a thinking machine. I think the correct answer in terms of how to make a thinking machine at the level of high-level methodology goes back to what Sam Adams was talking about earlier. You got to make an artificial baby, make an artificial pet, make bugs, make dogs, make birds, chimpanzees, make infants that are complete artificial idiots and can't do anything except hopefully amuse the person who's teaching them and playing with them. A baby is one of the stupidest things that I've ever seen. I mean, I've had 3 children, and they're all highly gifted and quite intelligent by this point. But when they start out, they just lay there and kind of defecate, urinate, and scream and wave their arms around, right? And part of the maturation process is just the unfolding of things that are pre-programmed in the genome. But a large part of it is learning. And we need a system that can start from a relatively ignorant state and actually learn how to do things. It doesn't start out knowing how to analyze genetics data or knowing how to drive a car. Let's say you take this idea, then you come up with an obvious question of where does the AI baby live? Is it a robot? Is it a search engine? I think building robots is a fundamentally good approach, but in practice, it's a pain to build robots. It's expensive. Sensor and actuator problems wind up taking up most of your time. The approach that we have settled on is experimenting with embodied agents in virtual worlds. So we're looking at this is a game engine, Crystal Space, that we've customized. This is a dog in Second Life, which is not something that we have built, but it's something that exists there right now. It's not a very smart system. It's a very simple expert system, but it's an artificial agent that can perceive, it can act, it can do things, it interacts. We have artificial birds, even artificial babies, and this was actually the tamest baby we could find in Second Life, which tells you something about the Second Life community. More interesting virtual babies, you're not tied to the humanoid form, and all kinds of creatures, as well as relatively normal-looking humans. So I feel working in virtual worlds gives you the ability to make systems that are perceiving, acting, communicating in language, embedded in a social network. Yet, there's big advantages over working with physical robots, one of which, from our point of view, is we have a distributed software team with people all over the world, and they don't all have to have robots in their labs and their home offices. They can collaborate in the same system. Another really interesting advantage, though, is the ability to roll out your virtual robots at low cost, potentially to hundreds of thousands or millions of users. If you create virtual babies and put them in virtual worlds online, in Second Life, in Club Penguin, in various video games, if you roll out virtual babies in this way, if they're amusing enough to play with, potentially you can get a huge mass of people teaching these babies things. And that's an advantage that AI just hasn't had in the past, having all these teachers. So you look at why might AI be achievable now when it wasn't achievable 10 years ago? Of course, there's a number of reasons. There's the brain emulation argument, which isn't the path I'm going down. There's just the fact that we have understood so much more of human cognition and cognitive psychology by now. There's the mathematical and AI tools we've developed in probability theory, evolutionary learning, formal logic. But there's also the fact that now, via the internet, we have the ability to harness the sort of wisdom of crowds, of a very large number of people teaching your AI system all at the same time, where all the knowledge it gains from all these people teaching it can be stored in a centralized place where it can all be reasoned on. And this is, to me, the most beautiful thing about the whole virtual worlds approach. Of course, all that is just methodology. With that methodology and that setup, unless you have the right design for a thinking machine, you're still not going to get anywhere. Just like a human body is nicely embodied, it has good sensors and actuators, but if you put ELIZA or Deep Blue inside a human head, it's still not going to be an AGI system. So my approach to the artificial general intelligence problem on a technical level is something I call the Novamente cognition engine. And this is a big, long story that I'm not going to be able to go into in the few minutes that are left to me here. But I'll say just a little bit about it that may be evocative for people who have some familiarity with the AI field already. The theory of mind underlying the Novamente system in itself is something that I worked on for about 10 years when I was an academic before entering the software industry. A summary of that is in a book called The Hidden Pattern that I published last year, which kind of elaborates a framework for understanding the mind, which views the mind as a pattern-recognizing system for recognizing patterns in the world and in itself, embodying the patterns it's recognized within itself, and then recognizing patterns among those patterns it's recognized. And what I do in this book is basically go through all the different aspects of intelligence that are known by cognitive psychology: perception, action, reasoning, learning, memory, emotion, will, and so forth, and try to explain them in a pattern recognition and formation framework, and a kind of grand unified vocabulary for understanding the mind, which doesn't tell you how to make a thinking machine, but it gives you a conceptual framework within which you can flesh out various AI designs. The Novamente AI design itself, just to go through some buzzwords describing it, it's not going to be much more than that. We use a knowledge representation, which is a mathematical structure called a weighted labeled hypergraph, which less formally means it's a bunch of nodes and links that are connected together. Some of the nodes refer to concepts that would have an English language label. Most of the nodes don't. They're just abstract stuff. Some can refer to percepts. Some can refer to actions. Acting on this collection of nodes and links, there are a bunch of cognitive processes, which we call mind agents. And the mind agents embody a bunch of different things. The key learning algorithms are something we call Moses, which is an improvement of genetic programming utilizing probability theory to learn more effectively, and something we call probabilistic logic networks, which I believe is the first system to fully integrate symbolic logic with probability theory. So these are the key learning algorithms. They work on the node and link knowledge representation, and they're embedded in a cognitive architecture which is largely inspired by the human cognitive architecture. And this is a block diagram that depicts the cognitive architecture at a very high level. I really don't think these diagrams tell you very much. What's important is what happens inside the boxes, and most of all, how the things inside each box really interact with the things inside the other boxes. In one of the talks earlier, we saw a similar diagram from Stan Franklin's LIDA architecture, and in fact, I've gone through in detail how you map my boxes into Stan Franklin's boxes. We're really saying the same thing. It's a breakdown of mind into perception, action, language, short-term memory, long-term memory, and the various parts that cognitive psychology has understood as being essential to how thought happens. And each of these boxes is filled in a certain way by a combination of our core learning algorithms, which is the Moses program learning approach and probabilistic logic networks. And it can be a little misleading when logic is mentioned, because that makes some people think of sort of old-fashioned AI systems. But although we use logic, the system is perceiving things through sensors, and it's controlling things through actuators. So it's it's not acting like a theorem prover. It's trying to understand the world as the world is presenting it to itself through its senses and understanding how to act. And for those who are interested in more fully understanding the Novamente approach, you can look at novamente.net, and there's some conference papers on there. So very quickly roll through a few other things. We're looking at potentially within the Singularity Institute rolling out a framework called OpenCog, and this would be an open source approach to general intelligence. I would take some of the components we've developed in the Novamente system, which is a proprietary system, clean them up a bit, release them open source, the knowledge representation, some of the key learning algorithms, not the framework for controlling agents in simulation worlds. The idea would be to give a kind of playground that AI researchers within the community could use to develop their AI algorithms in a more AGI-oriented way, so the different AI algorithms can interact with each other and be more fully fleshed out. Another interesting avenue is to release AI components in a way that can run on a variety of machines on all of your desktops, which is a potential Singularity Institute initiative we call AGI at Home. So I'll wrap up just by giving a pictorial overview of the ladder of increasing intelligence as we're looking at it. We can start off, say, with something like virtual pets, virtual ambient animals running around in simulation worlds, which you can train and which interact with you. Move on to something like virtual parrots that can talk. They can learn more language by having hundreds of thousands of people interact with them and teach them. Move on to virtual babies, human babies, alien babies, virtual human beings. Then beyond there, we can move on to virtual superhumans. Virtual superhumans plugged in with AIs, hybrids, of course. And finally, what's the end goal? Of course, the end goal is something vastly transhuman. That's a graphic I got from the online textual virtual world Orion's Arm. This is supposed to be a superhuman god cluster. And this finally leads on to the ethical issues involved, which I've left to the very end, so I have no time to talk about them. So don't worry about it. Leave it all to us. Now, more seriously, I need to give at least 30 seconds to ethical issues. I think it's very easy. It's very easy to think in a cavalier way about how cool it would be to create a superhuman God intelligence, and of course it would be. I would consider that very fitting as my life's work. You know, on the other hand, there are major dangers involved here, which you can't shrug at either. And I find it's more easy to shrug off the human race in some ways than to shrug off yourself and all the people that you know and love, which is sort of well-known cognitive error. We find it hard to conceive of a catastrophe on a really, really massive level. Yet if you think about each individual person who could be threatened if AI went the wrong way, it becomes sort of more amenable to our empathic system to understand. So I think about my own family. Do I want my kids and my wife to be wiped out by an AI program that I create? Well, you know, I don't even want them to be run over by a car, let alone have all of them wiped out by an AI program. And this leads into some very difficult problems. How do you make an AGI system so that it's not only intelligent, but as it makes itself smarter and smarter and ascends to the superhuman God level, it doesn't lose its original goal system, which presumably includes being fairly nice to us measly little hyper-cerebral monkeys. And if you've figured out how to do this, how do you ensure that that's the AGI that gets built instead of some other AGI that someone else created, which isn't as friendly? And these are very hard problems and are among the reasons that the Singularity Institute for AI, which is put on this conference, exists. I know in my work in Novamente, building a proprietary AGI system, we're pushing hard to create our own thinking machine. And being a startup company strained for resources, we don't often have time to worry about these pesky little questions of how to ensure that your AGI is really nice to people once it ascends to the superhuman level. But there are really no more important questions for people to be thinking about right now. And I'm very glad that the Singularity Institute exists to focus on these things. So those of you who live in this area may be interested to go to the Virtual Worlds Conference, which is in San Jose on October 10th, where we hope to be giving a preview of a Novamente-controlled virtual agent in Second Life. And the AGI 08 conference in March in Memphis shouldn't be forgotten either. All right. Sorry, I went a little over time. All right.